What's up guys, this is Masi. Welcome to my channel. In this video I start the section 2 of chapter 7 from chemistry 12, and the chapter is about equilibrium law and the equilibrium constant. In the mid 1800s, two Norwegian chemists, Guldberg and Wag, conducted detailed studies on chemical equilibrium systems, and based on their observations they were able to describe the chemical equilibrium in a closed system in a mathematical way. The mathematical description is known as the equilibrium law, and the equilibrium law is sometimes also called the law of mass action. What is the equilibrium law and why is it useful? To start our discussion, suppose that A, B, C, D are chemical entities in gas or aqueous states, and that lowercase a, b, c, d are the coefficients in the balanced chemical equation. We can now represent the chemical equilibrium system by this general chemical equation. AA plus BB gives CC plus DD, and we consider it as reversible reaction. The equilibrium law for this general reaction may be represented quantitatively by the following mathematical equation. K, which we will see later on, is equilibrium constant. It's equal to C to the power of C, D to the power of D over A to the power of A times B to the power of B. So basically all capital letters A, B, C, D are chemicals, A, B are reactants, and CD are the products, and the lowercase are their coefficients after balancing the chemical reaction. So basically K is going to be the products divided by reactants, and each of them is to the power of their coefficients. So the square brackets in the equation indicated the concentrations of the chemical entities at equilibrium. So when you will see anything in bracket, square bracket, it means that we are talking about their molar concentration at equilibrium condition. So K is the symbol for the equilibrium constant, and a constant numerical value that defines the equilibrium law for a given system. Since the units of the equilibrium constant vary according to the values of A, B, C, D, equilibrium constant values are usually reported without units, because it's different based on different reactants or products and their coefficients. So far we can say that the equilibrium law is the mathematical description of the chemical system at equilibrium, and equilibrium constant, a constant numerical value defining the equilibrium law for a given system, and units are not included when giving the value of K. Now analyzing the equilibrium law. To see how the equilibrium law is useful, consider the formation of hydrogen iodide gas, which is Hi, from its elements. The balanced chemical equation for this reaction is H2 plus I2 gives 2Hi after balancing them. Table 1 shows the results for an investigation to observe how changing the initial concentration of the reactants and products affected the equilibrium. The reaction was allowed to proceed to equilibrium in a sealed 2-liter flask at 485 degrees Celsius. So we have 3 trials, 3 experiments. So we list them here, the initial concentration of all of them for H2, hydrogen, for iodine, and Hi. So as you see here, for the first one, the initial concentration of H2 and I2 are 2, and there is no Hi at initial condition. For the second one, we have Hi, but we didn't have any hydrogen or I2. And on the third one, we have some I2 and some Hi, but we didn't have any H2. And as you see here, at equilibrium concentration, we have this different equilibrium molar concentration. So in table 2, the data from each trial were entered into an equilibrium law equation, and what do you notice about the value of equilibrium constant? So let's calculate each of them separately, and based on the equilibrium we had earlier, the equation we had earlier, which is this one, we can calculate all the k values for these three different trials. So for the first one, we just sub all these numbers. We can have 3.119 squared divided by 0.44 times 0.44. The k value is 49.8. The second trial, we have 1.56 to the power of 2. Why to the power of 2? Because here the coefficient of hi is 2. For I and for I2 and H2, the exponent is 1. Why? Because the coefficient is 1 here. And for the third trial, we have 0.28 squared divided by 0.045 times 0.035. So as you see here, we have exactly three values, and all of them are exactly the same. So the equilibrium constant value is the same, 49.8, for all three trials. The equilibrium constant will always have the same value of 49.8 regardless of the initial concentrations, provided that all other variables are kept the same. Chemists have found that this holds true for any specific chemical reaction at equilibrium at a given temperature, and the value of the equilibrium constant remains the same regardless of initial concentration. However, the value of equilibrium constant depends on the reaction temperature. In table 3, notice how the equilibrium constant value changes with temperature with gaseous nitrogen and hydrogen are combined in a closed vessel and reacts to form ammonia. So as you see here on the left hand side, we have equilibrium constant for the production of ammonia gas from elemental nitrogen and hydrogen at various temperatures. So as you see here, for three different temperatures, we have three different values for K. So for example, for 25 degrees, we have 4.26 times 10 to the power of 8. Now, writing equilibrium law equations and calculating K. In section 7.1, you saw that the equilibrium position of the reaction describes their relative concentration of reactants and products in a chemical reaction system. By convention, the equilibrium position is expressed as being far to the right toward products or far to the left toward reactants. The equilibrium constant K can be used to determine the equilibrium position of the chemical reaction system. You will calculate the equilibrium constant from the equilibrium law equation in tutorial 1. Always use amount concentration of the reactants and products at equilibrium condition. At equilibrium in the equilibrium law expression calculation. Remember that in this textbook, the concentration of aqueous solution and gaseous substances are provided in terms of mole per liter. Tutorial 1. Write here an equilibrium law equation from a balanced chemical equation. So we have this chemical reaction, 4 ammonia plus 7 O2 gives 4 NO2 and 6 H2O, and we have a reversible reaction. So we need to find K value. So we need to write the equilibrium law equation because we don't have any equilibrium concentration right now. So we just need to write the equilibrium law equation. So as you see here, if we go back to the original equation we had, we need to write the products on numerator, and then in denominator we put the reactants. And for each chemical, we need to have the coefficient as exponent. So we have the product is NO2 to the power of 4 times H2O to the power of 6 divided by NH3 to the power of 4 times O2 to the power of 7. So that is the equilibrium law equation for this balanced chemical equation. Let's go for the second one. Now we need to calculate K for the synthesis reaction. In a closed vessel at 500 degrees Celsius, gaseous nitrogen N2 and hydrogen combine in an equilibrium reaction to form ammonia gas, which is NH3. So N2 plus 3H2 gives 2 moles of NH3. The equilibrium concentration of gaseous nitrogen and hydrogen and ammonia are provided here. 1.5 times 10 to the power of negative 5 is gaseous nitrogen. 3.45 times 10 to the power of negative 1 mole per liter is concentration of hydrogen at the equilibrium. And finally 2 times 10 to the power of negative 4 mole per liter is equilibrium concentration of ammonia. Then we need to write down the equilibrium law equation based on the formula here. NH3 to the power of 2 divided by N2 to the power of 1 because the coefficient is 1 times H2 to the power of 3. And then all the molar concentration and equilibrium are given. We just sub it in here and then find K value. So the K value is 6.49 times 10 to the power of negative 2. Next one, calculating K for the decomposition reaction. We have in a closed vessel at 500 degrees Celsius, we have ammonia gas will decompose into its elements. 2 ammonia gas is decomposed to nitrogen plus 3 moles of hydrogen. And the molar concentration are given at equilibrium. We have this for nitrogen, for oxygen, for hydrogen, and for ammonia. So if we want to write the expression, we have N2 to the power of 1, H2 to the power of 3 divided by NH3 to the power of 2. And then we sub all the equilibrium concentration. For N2 we have this one, for hydrogen we have this number to the power of 3 divided by 2 times 10 to the power of negative 4 to the power of 2. So the K is going to be 15.4. So the equilibrium constant K for the decomposition of ammonia at 500 degrees Celsius is 15.4. Now if you compare the two equilibrium constants that you calculated in sample problems 2 and 3, the two previous examples, you can see that they are very different. However, these values are mathematically related. Why they are mathematically related? Allow K to represent the equilibrium constant of the forward reaction and the formation of ammonia gas, and then let K prime represent the equilibrium constant of the reverse reaction. So as you see here, the K for the first one is 6.49 times 10 to the power of negative 2, and the second one was 15.4. Now as you see here, one of them is inverse of the other one. Why we have this kind of relationship? Because in the second example we had decomposition of ammonia, everything is the same, temperature is the same. On the second example we had synthesis of ammonia at the same temperature. So it means that the K values of these two examples are inverse of each other. So we can say K equals to 1 over K prime. Now in this part we have equilibrium constant and reaction rate. When a reversible chemical reaction is at equilibrium, the rate of the forward reaction is equal to the rate of reverse reaction. So at equilibrium, as we had it earlier, the rate of forward reaction is equals to the rate of reverse reaction. Now we can show why this is true. Consider a hypothetical reversible reaction in which reactants AB form products C and D. Since it is a reversible chemical reaction, dynamic equilibrium is achieved when the forward reaction proceeds at the same rate as the reverse reaction. So the chemical equation for the forward reaction of the chemical equilibrium system is AB gives C plus D. Assume that this reaction is an elementary process, which is a chemical process that is completed in a single step. Recall from chapter 6 that in a dilute solution, the rate of a chemical reaction is proportional to the amount of concentration of reactants. If K of F is the rate constant for the forward reaction, we can write the rate of reaction as this. K forward reaction rate equals to Kf times concentration of A times concentration of B. Similarly, we can do the same thing for the reverse reaction. For the reverse reaction given by the chemical equation, C plus D gives A plus B. So we can have another chemical reaction, and we use the reaction constant as Kr. If Kr is the rate constant, then this equation represents the reverse reaction rate. Reverse reaction rate is Kr times C times D. So at equilibrium, the forward reaction rate must be equal to the reverse reaction rate. So the forward equals to the reverse reaction rate. So we can say Kf divided by Kr equals to C times D divided by A times B. Cross multiplication, we have exactly the same thing. The ratio is the same as the equilibrium law equation for our hypothetical equilibrium system. Therefore, the ratio of the reaction rates or rate constants of the forward and reverse reaction is equal to the equilibrium constant. So for simple reversible reactions in which all the coefficients are 1, we would also arrive at this equation by replacing the coefficient of 1 in the equation originally proposed by the chemists Goldberg and Vogt. So K will be equal to C to the power of C times D to the power of D over A to the power of A and B to the power of B. However, this mathematical relationship is true only for elementary processes. Most chemical reactions are not elementary processes. This part I want to talk about heterogeneous equilibria. The chemical equilibrium systems that we have discussed so far have been examples of homogeneous equilibrium. So basically we divide equilibrium into two different classes, homogeneous and heterogeneous, or we can say homogeneous reaction and heterogeneous reaction. So what is the difference between homogeneous and heterogeneous reaction? In homogeneous, all reactants and products in the system were in the same state of matter. For example, all reactants and products are aqueous solution. But in heterogeneous, they are not in the same phase, or they are not in the same state of matter. We might have solid and gas, or solid and liquid, solid and aqueous solution. So in this kind of examples, we call it heterogeneous equilibria or heterogeneous reactions. When the reactants and products in the chemical equilibrium system are present in more than one state or more than one phase, the system is a heterogeneous equilibrium. For example, calcium carbonate CaCO3 in solid phase can undergo a reversible decomposition reaction to form solid calcium oxide, CaO, and carbon dioxide gas. So as you see here, CaCO3S solid, we have a reversible reaction CaO S plus CO2 gas. This reaction is used in a commercial preparation of calcium oxide, also known as lime, from calcium carbonate sources such as limestone. Lime has many uses, such as in the manufacturing of steel and plastics. Straightforward application of the equilibrium law leads to the equation K equals to CO2 times CaO divided by CaCO3, and obviously all these square brackets are molar concentration at equilibrium condition. However, the equilibrium position of a heterogeneous equilibrium doesn't depend on the quantities of pure solids or liquid. The fundamental reason for this behavior is that the concentration of pure solids and liquids cannot change. In a reversible decomposition reaction of calcium carbonate, the concentration of calcium, solid calcium carbonate, and solid calcium oxide remain constant. So basically, we just write this equilibrium concentration only for gases and also for aqueous solutions. So we don't write it for liquids and we don't write it for solids. Why? Because as we said, the concentration is not changing, and the concentration of pure solids and liquids cannot change. So that's very important that we can highlight it. The concentration of pure solids and liquids cannot change. In a reversible decomposition reaction of calcium carbonate, the concentration of solid calcium carbonate and solid calcium oxide remains constant. If we represent this constant concentration by a symbol of C1 and C2 respectively, we can write the equilibrium law equation as K equals to CO2 times C1 divided by C2, which are not changing. C1 and C2 are not changing. Since C1 and C2 are constant and K is also a constant, we can simplify the equilibrium law equation by including all of them together. So we can then write the equilibrium law equation for this reaction as K equals to the concentration of CO2, which is a gas. So we can write the following generalization for this analysis. If pure solids or pure liquids are involved in a chemical equilibrium system, their concentrations are not included in the equilibrium law equations for the reaction system. So we cannot simplify the equilibrium law expression for solutions or gases, since the concentration of substances in these states can vary. Therefore, carefully note the states of all substances in a reaction system. For example, consider the decomposition of liquid water to gaseous hydrogen and oxygen. So 2H2O gives 2H2 plus O2. The equilibrium law equation for this reaction is H2 to the power of 2 times O2. Why? Because here on the left hand side we have liquid and we don't write it for liquid. So we didn't include water in the equation because it is a pure liquid. However, we could instead carry out the reaction under conditions where water is in a gas state. So 2 water in gas state, it gives 2H2 plus O2. In this case, we can include water as well because we have the gas phase. So K equals to H2 to the power of 2 times O2 divided by H2O to the power of 2. Now for tutorial sample problem 1, a reaction system with a pure solid and pure liquid. Solid phosphorus pentachloride PCl5S can undergo a reversible reaction to form liquid phosphorus trichloride PCl3 liquid and chlorine gas. Write the equilibrium law expression for this heterogeneous equilibrium. So basically, since PCl5 and PCl3 are solid and liquid, we don't consider them at equilibrium law. So we write the balanced chemical equation and we don't consider the liquids and solids. So K will be only based on Cl2, the concentration, and the exponent is 1. Why? Because in the balanced chemical reaction we have the coefficient as 1. Now sample problem 2. A reaction system with 2 pure solids. When deep blue solid copper 2 sulfate pentahydrate CuSO4 5H2O is heated to drive off water vapor H2O gas, white solid anhydrous copper 2 sulfate CuSO4S is formed. The reaction is reversible. Write the balanced chemical equation and the equilibrium law equation for this reaction system. So it's going to be CuSO4.5H2O gives CuSO4 plus 5H2O. So here we have 2 of the compounds are solid, so we don't consider it for the equilibrium law. So we can say K is equal to H2O to the power of 5. The magnitude of the equilibrium constant K. We have seen that the magnitude of the equilibrium constant K can vary significantly. What does the magnitude of the equilibrium constant tells us about the equilibrium system? To answer this question, consider the reaction of carbon monoxide gas CO with oxygen gas O2 to produce carbon dioxide gas or CO2 gas. This reaction contributes some of the carbon dioxide gas released into the atmosphere by internal combustion engines in figure 4. The balanced chemical equation for this reaction is 2CO plus O2 gives 2CO2. So when this reaction is conducted in a sealed vessel at 25 degrees Celsius, the equilibrium constant is 3.3 times 10 to the power of 91. Therefore, the equilibrium law equation can be written as follows. K equals to CO2 to the power of 2. Why to the power of 2? Because the coefficient is 2. Divided by the reactant sides, we have CO to the power of 2 times O2 to the power of 1. That's going to be equal to 3.3 times 10 to the power of 91. Looking at the equilibrium law equation, the numerator includes the equilibrium concentration of the product and the denominator includes the equilibrium concentration of the reactants. The very large value of the equilibrium constant indicates that the equilibrium position is significantly toward the right. We can therefore predict that at equilibrium, the concentration of carbon dioxide gas, which is the product, will be much greater than the concentration of carbon monoxide gas and oxygen gas, which are the reactants. In contrast, the reversible reaction of nitrogen dioxide gas with nitric oxide gas, NO, to form gaseous dinitrogen monoxide and oxygen, as you see here. When we write the equilibrium constant, we can say N2O times O2 divided by NO2 times NO equals to 0.915, which is very small. Since this equilibrium constant is close to 1, the concentration of the product at the equilibrium is approximately equal to the concentration of the reactants. So finally, let us look at the equilibrium constant for a reversible thermal decomposition of water at 1000 degrees. The balanced chemical equation and the equilibrium law equation for this reaction are as follows. 2H2 gives 2 moles of hydrogen plus 1 mole of oxygen. So when we write the K formula, we have H2 to the power of 2 times O2 divided by H2O to the power of 2. And the K is going to be 7.3 times 10 to the power of minus 10. So the value of the equilibrium constant for this chemical reaction system is extremely small. This means that the concentration of water vapor is much larger than the concentration of hydrogen gas and oxygen gas at equilibrium. At this temperature, the equilibrium position is toward the left and highly favored the reactants. Table 4 summarizes the relationship between the magnitude of the equilibrium constant value and the equilibrium position. So when K is much greater than 1, the equilibrium position is far to the right, favors products. When K is approximately equal to 1, equilibrium concentration of the products similar to the concentration of reactants at the equilibrium concentration. And when K is much less than 1, the equilibrium position is far to the left, which is favoring the reactant side. So this is the end of this section 7.2 from Chemistry 12 Nelson. I hope you enjoyed this video. Please leave me a comment if you have any question and I get back to you as soon as possible, and please don't forget to subscribe this channel. Thank you.